Great. Hi, everybody, and thanks for joining us for this month's Wednesdays with Bing. Today, we have Sean Watson joining us from the University of Glasgow. Sean has an MEng in civil engineering from the University of Glasgow, and he's currently a PhD candidate at the same university, where he has been investigating the potential deep geothermal energy resources beneath Glasgow. He's been involved and made a significant contribution to the development of the heat map for Scotland, and he is currently working as a research assistant developing digital twins to optimise the energy performance for new campus buildings at the university. And I will hand over to Sean. Take it away.
Thanks very much for the introduction, Helen. And good afternoon, everyone. Nice to meet you all. Thanks very much for the opportunity to discuss my research with you today. I'm going to present the findings of a research project that I was involved in a couple of years ago in 2019, over a 6-month period, where we looked at the scope for repurposing onshore hydrocarbon wells in the UK for geothermal energy production and storage. The research was funded by the Engineering and Physical Sciences Research Council and the National Centre for Energy Systems Integration. It was led by Professor Joy Falcone and Dr. Rob Westerby from the University of Glasgow, and our project partners were Perenco and Schlumberger, whose insight into the sector and data and advice was really invaluable through the project. The research so far has resulted in 2 publications, one of which was a conference proceedings paper at the World Geothermal Congress, and the other is an open access paper published in Energies last year. So I'll be presenting the work from both of these papers and referring to them throughout. I'll stick the details up again at the end of the presentation for the references. To begin, I'd like to present a brief overview of the background of the project. Geothermal energy exploration is driven by the need to supply low carbon energy, which is becoming increasingly important in the UK energy mix, particularly given the need to address the energy trilemma. That's providing sustainable, equitable and secure energy supply. To date, research and exploration of geothermal resources within the UK has been targeted at flooded abandoned mine workings, hot sedimentary aquifers within Mesozoic and Paleozoic sedimentary basins, and buried radiothermal granites, and the distribution of these are shown on figure 1. The development of geothermal projects in countries such as the UK are hindered by a combination of social, technical, economic and regulatory barriers. The most significant issue is recognised as economic, due to the capital costs of drilling being such a high proportion of project lifecycle costs. One potential solution is to repurpose onshore hydrocarbon wells for geothermal heat production and/or storage. The UK has more than 2,000 onshore hydrocarbon wells, many of which are drilled within the sedimentary basins, which may be targeted for geothermal exploration, shown in the figure. Given the regional geothermal gradients and heat flows within sedimentary basins in the UK, onshore hydrocarbon wells may be suited for geothermal repurposing, adding additional value to previous capital expenditure. However, the current UK regulatory framework does not allow geothermal coal production from existing hydrocarbon wells, nor the retrospective repurposing for geothermal use. As once hydrocarbon production ceases, wells must be plugged and abandoned by the operator. In this study, it is assumed the regulations will be changed in the future in recognition of the added value of repurposing hydrocarbon wells. The wealth of infrastructure, expertise and subsurface data that exists within the UK onshore hydrocarbon sector potentially provides a formidable asset for the development of low carbon geothermal energy resources in the UK. Previous consideration of geothermal repurposing of hydrocarbon wells is concentrated on the generation of electricity. Some jurisdictions offer subsidies for geothermal electricity, reflecting its potential contribution to the environmental benefits of decarbonisation. However, in the UK, no specific subsidy exists. Furthermore, when this research was carried out, the UK had 14 gigawatts of offshore and 10 gigawatts of onshore wind generating capacity, with the government committed to expanding the offshore capacity to 40 gigawatts by 2030. Therefore, adding a small component of geothermal electricity generation to this would make no significant difference towards the overall decarbonisation achieved. Whereas much less progress has been achieved towards the decarbonisation of heat in the UK, despite it representing around 45% of the total energy demand. Geothermal heat therefore offers the possibility of making useful contributions to the decarbonisation of UK energy supply, as it has many potential end uses, such as district heating for domestic water and space heating, the provision of heat to swimming pools, greenhouses, aquaculture and industrial processes, for example. So there's no global inventory of hydrocarbon wells, to my knowledge, but estimation on the basis of available data, including the many tens of thousands of oil and gas fields worldwide and the circa 1 million operational offshore wells in the US alone, the potential worldwide number of wells available for geothermal repurposing for heat is in many millions. A significant resource therefore exists, and we envisage its development will involve many steps, including demonstration projects and pilot projects. As an initial step towards this in the UK, this research investigated the most favourable candidate sites for geothermal repurposing of onshore hydrocarbon wells. In addition to providing results identified in UK onshore fields with the greatest potential for repurposing for heat, this study demonstrates a workflow that is more applicable elsewhere. So in this presentation, I will summarise the technological options for geothermal repurposing for hydrocarbon wells. Then I go on to discussing our work on assessing favourable candidate sites in the UK where onshore hydrocarbon wells could be repurposed for geothermal energy production and storage. And this was achieved in 3 stages. First, a screening survey was conducted of potential candidate sites using GIS mapping and the compilation of databases from available public domain information. And then second, the most favourable candidate sites were selected for further analysis, which included detailed calculations of the potential heat output from the wells. Then a decline curve analysis of production rates was conducted to extrapolate geofluid production to determine the recoverable heat resources and the end uses that might be sustained over an assumed project lifetime. And then finally, the technical and environmental constraints affecting the use of available heat were discussed. So I'll just give a quick overview of the different technologies that are available in terms of repurposing hydrocarbon wells. First, the geothermal potential of hydrocarbon wells has been investigated by several authors, with pilot projects implemented worldwide and pre-feasibility studies carried out. As mentioned previously, although offshore hydrocarbon fields offer geothermal energy potential, it's likely that only electricity generation would be appealing in such remote environments and exclusively for in-project utilisation, unless interconnect and export has become available. However, previous studies onshore in the UK, such as in East Midlands Petroleum Province, have shown opportunities may exist whereby onshore hydrocarbon wells could be repurposed to provide geothermal heat, which may make significant contributions to the local heat demand. And this could be done for mature producing onshore fields where hydrocarbon operations could continue, but with the inclusion of geothermal infrastructure, as studied at the Rich Farm field in the Wessex Basin and in the Jakarta Via Fortuna field in Italy. Depending on its temperature, the substantial volume of co-produced water presents opportunities for electricity generation and direct use of heat by nearby users. This is the potential for reducing operational costs, extending the hydrocarbon field life, improving ultimate hydrocarbon recovery, and delaying decommissioning liabilities. Then eventually, depending on the long-term infrastructural integrity and regulatory framework, the hydrocarbon operator could transfer the fields to a geothermal operator. And for abandoned exploration wells or wells that have ceased hydrocarbon production, there are a variety of technological options for repurposing. For example, a well might be re-drilled into a deeper aquifer zone to enable some wells in a field to be converted to geothermal production wells and others to water reinjection wells. This option could likewise be used for aquifer thermal storage. Another option might be to drill multiple slim lateral holes from an existing or deepened well to increase water withdrawal, as the original mother bore completions could host more water following the depletion of hydrocarbons. An alternative to re-drilling a well might be to recomplete it as a closed-loop well-bore heat exchanger, although this would depend on favourable geological conditions and local heat requirements. Application of this technology would remove the cost of drilling a new deep geothermal well, and if required, enlargement of the near wellbore region could be conducted to artificially enhance thermal properties. And just in terms of the research conducted, starting with public domain data sets, the first objective of the study was to conduct a screening survey of candidate sites with the potential for geothermal repurposing. The UK currently has no dedicated mapping tool or mechanism to assess the potential geothermal resource at any location, such as that, like thermal GIS in the Netherlands and equivalent GIS tools in Germany. So to enable this study to map potential candidate sites, we produced a GIS model combining the geothermal data in the UK with public domain data from onshore wells and production data from onshore fields, which were obtained from the Oil and Gas Authority. The GIS model integrated information such as the location, depth, operational status and bottom temperature for onshore hydrocarbon wells with production rates from onshore hydrocarbon fields, as well as the extent and depth of potential geothermal aquifers across the UK. Several screening criteria were then assessed, and the most favourable candidate sites were selected for further analysis and detailed calculations for potential heat output, and then also the end users that could be sustained, as I mentioned previously. So I'll just talk you through the screening survey that we conducted first of all. So to begin, the depth and operational status of each onshore hydrocarbon well was assessed on a well-by-well basis. To enable this, a database of all 2,242 UK onshore hydrocarbon wells were compiled using the OGA's online data centre and public well search tool to obtain information. These will be mapped on figure 2 here. Data such as the depth of the well and operational status, however, were not included in the publicly available downloadable databases and GIS shape files in OGA's online data centre at the time of the research. And as these were kind of crucial parameters to assess in the study, I had to individually search for each well on the OGA's website using a wellbore search tool, just using the registration number of the well, which is quite a painstaking process to get the operational status and depth of each well, and then add them into the database. But yeah, it was crucial to do. But I now notice actually that the OGA have included data such as this in their publicly available downloadable data. So I would have said there's a couple of weeks of work if that was the case back in 2019. However, following the compilation of the database, the criteria could then be applied to select potential candidate sites. So considering operational status, first of all, the operational status of hydrocarbon wells in the UK are reported by the OGA's Well Operations Notification System, In this system, wells are classified as drilling, operating, shut-in, plugged, or abandonment phase 1, phase 2, or phase 3. A lot of that's self-explanatory, but I'll just run through it just for information. So drilling denotes a well that is under construction. Operating denotes a well is operation for some purpose, such as hydrocarbon production or water injection. Shut-in denotes a well that is shut in either at the wellhead or at a subsurface safety valve. And plugged means that the reservoir has been isolated from the surface, potentially temporarily. Abandonment phase 1 means that a permanent barrier has been installed in the well to isolate the reservoir. Phase 2 means that the reservoir and all permeable zones above it have been permanently isolated from each other or from the surface. And phase 3 means that the surface insulation at each well site has been removed and will never be used again. So considering all of this, to screen the candidate sites by operation status, wells at abandonment phase 2 and phase 3 were disregarded because we kind of assumed that these were not viable for repurposing. However, wells at phase 1 of abandonment were retained because although the hydrocarbon reservoir has been made permanently inaccessible, such a well could potentially be repurposed with a closed-loop water heat exchanger, for example. And then when screening by depth, wells with a true vertical depth of less than 500 metres were disregarded because this is the threshold value which reflects the regulatory boundary between shallow and deep geothermal wells in the UK under the UK Renewable Heat Incentive Subsidy Scheme. So applying the depth cut-off and also the screening of the operation status, the number of candidate wells were reduced from the original 2,242 shown in figure 2A to 560 shown in figure 2B. The next criteria we assessed were the temperature of the co-produced water and also the proximity of the well, hydrocarbon well, to potential geothermal aquifers. This involved more development of the GIS model. For example, in terms of the temperatures, what we did was use previously published data both on regional geothermal gradients derived from onshore hydrocarbon wells, such as those in the East Midlands Petroleum Province, and studies by Gathurst and John Glaze, references of which are included in both of the papers related to this work, and also maps of the temperature at 1 kilometre depth beneath the UK from publication by John Busby in 2011. Again, references are available from this. So what we did was, in terms of the map of the temperature at 1 kilometre depth, I georeferenced that in GIS software and essentially redrew all the contours as polygons, which then meant that once you overlaid the location of the hydrocarbon wells, you could attach the temperature at 1 kilometre depth to each well. Then, assuming a nominal surface temperature of 10 degrees, you calculate the geothermal gradient and then extrapolate that to the true vertical depth of the well to obtain an estimate of the bottom temperature. So there's uncertainties within these calculations which should be noted. First of all, for more detailed analysis, the harmonic mean thermal conductivity of each part of the geological sequence at the site should be established to account for variations in the geothermal gradient due to changes in stratigraphy. And also geothermal gradients should be corrected for the effects of paleoclimate, which are particularly influential in the UK. And as a result, some of the vulnerable temperatures estimated in our survey may be underestimated. And we also developed the GIS model of the extent and depth of the potential geothermal aquifers in the UK, as shown in figure 4. This was based upon work that was previously conducted by Downing and Gray in 1986 during investigations of the potential geothermal energy resources in the UK during the 1980s. And they mapped the potential geothermal resources in Mesozoic and Paleozoic basins through the UK, and also highlighted potential geothermal fields, which they determined as aquifers which have are deep enough with a suitable temperature above 40 and above 60 degrees, and with the transmissivity enough to be capable of supporting a geothermal exploration. So yeah, we again georeferenced those maps and implemented into the GIS model, overlaying the hydrocarbon wells to assess the proximity of the well to the aquifer, and then that led to the opportunity to assess which wells already intersected potential aquifers, which ones could be deepened to then intersect the aquifer. So the results of this are shown here in this slide. In terms of the temperature, there were 493 wells with an estimated bottom temperature greater than 40 degrees, 102 of which had an estimated bottom temperature of over 60 degrees. And high-ranking candidates sites include those at Gaythorpe, Headington, Kirby-Nisperton, West Newton and Witch Farm. And these were decided these were the most optimal because of their operation status, either being operating shut in or at abandonment phase 1. And then in terms of the proximity of the wells to potential aquifers, found that there were 231 candidate wells located within the potential geothermal fields, which were denoted by Downing and Gray in 1986. And high-ranking wells which are contained in these hotspots include those from Wareham and Witch Farm down in the Wessex Basin, and Gaythorpe, Everston, Headington, Marishes and West Newton, East Yorkshire and Lincolnshire. But it was then decided that the focus of the remainder of the work should be on hydrocarbon fields and wells where the possibility may exist for them to be recovered from coal-produced fluids. So the next screening criteria assessed was the water production rate from the field. This was based upon production rates from each onshore field in the UK, which again we obtained from the Oil and Gas Authority. The 10 onshore fields with the highest annual water production rates were ranked, and then combined with data on the operational wells, the bottom hole temperatures calculated of the fields, and were then ranked in terms of those with the greatest potential for geothermal repurposing, as shown in this slide here. The most suitable candidates were Witch Farm, Stockbridge and Wareham in the Wessex Basin, and Welton in the East Midlands Basin. Then two of these, Witch Farm and Wareham, were selected for more detailed analysis, and I'll go on to explaining a bit more about this now. So Witch Farm field in the Wessex Basin is the largest onshore oil field in Western Europe and has a significantly higher water production rate and many more operating wells than any other onshore field in the UK, as we discussed previously. In addition, the estimated reservoir temperature is high enough to support potential applications of the recoverable heat on the co-produced water. The Witch Farm field was developed mainly in the 1980s and 1990s. Production started in 1978 and peaked in the period 1996 to 1997. But the field now is experiencing declining production and is heading towards decommissioning. Production is primarily from the Triassic Sherwood Sandstone Formation, which is at 1,580 metres depth and yields temperatures of 65 degrees, with subsidiary output from the Jurassic Aged Bridport Sand Formation, which is found at 920 metres depth and yields a temperature of 44 degrees. The Witch Farm onshore facility consists of a tieback of well sites to a central gathering and processing station. The produced fluids are then transferred from the well sites to this gathering station via pipelines. So after which oil is sent via pipeline to oil terminal in Southampton. Natural gas is sold to the Southern Gas Pipeline, and LPG is exported by road tankers. All produced water is treated and injected, and the wells produced with the aid of thermal pumps. In relative close proximity to Witch Farm is the Wareham field. The Wareham field produces from the Bridport sand formation into production and injection well sites. Fluid produced at the WC site, which you can see on figure 8, is piped to the Wareham B site, where it's commingled with production from both sites and exported to the Witch Farm gathering station. In 2016, the operator of the field was granted permission to extend the life of Witch Farm until 2037. So on the basis of this, and from the results obtained from the screening exercise earlier, we decided that these two fields were suitable for more detailed analysis of the potential heat outputs. To do this, we conducted a decline curve analysis, which was applied to both Witch Farm and Wareham to predict field performance until the year 2037. Just shown an example of this for Witch Farm. Decline curve analysis is a standard method for evaluating the future production potential of hydrocarbon wells, and in this analysis it has been assumed that all currently operating wells remain active until 2037. Given the declining and considerably smaller oil flow rates, as well as the lower capacity of oil, lower heat capacity of oil compared to that of water, only the forecast water production has been considered and has been used to calculate the thermal output of the Witch Farm field. The results of these calculations of thermal output indicated that geothermal repurposing of the Witch Farm field may yield thermal power outputs of around 90 megawatts. Theoretical examples of notional uses of this recoverable heat from Witch Farm includes horticulture, heated swimming pools, aquaculture, and the provision of heat to breweries, fermentation. For example, it was estimated that the thermal power output could be utilised to provide heat to around 150 greenhouses or 99 swimming pools. And the calculations of these are included in the Watson et al. 2020 Energies paper. So based upon all this, it's clear that the Witch Farm field would be a very strong candidate for geothermal repurposing. However, there are environmental barriers to any future repurposing of the hydrocarbon infrastructure at this field. This is because Witch Farm is located within the Dorset area of outstanding natural beauty, and therefore any developments are subject to strict planning guidelines. This means that whether a project receives planning permission is dependent upon whether it is deemed to achieve a favourable balance between the benefit of providing low carbon heat and the downside of environmental impact. The Wareham well sites, however, are located just outside of this protected area. So geothermal projects exporting heat from the produced geofluid there would encounter pure planning issues. However, as shown in Table 4, the recoverable heat from Wareham is considerably less than that from Witch Farm, which limits the potential end uses heat available at this site, given the low temperature and low production rate from the field. However, in principle, a solution to deal with the sensitivity of the area surrounding Witch Farm might be to install a highly insulated pipe to transport hot water in a clean loop after using the heat exchanger, and then passing it to Wareham or another locality where there's potentially high heat demand. However, the high overhead costs might make this almost non-viable. Nonetheless, setting this issue aside just now, potential end use for the heat from witch farm transported via a network of pipes might be able to provide heat for amenities such as swimming pools and hotels in the nearby resort town of Swanage and neighbouring tourist villages on the south coast of England. However, given the environmental kind of constraints, the use of routes such as in greenhouses, which would have been ideal given the kind of rural nature of the site, would have to be excluded in this instance. To round off, we then considered how the heat resources from Wareham and Witch Farm compare with those available from other low temperature geothermal heat projects. Results of this comparison, shown in the graph in figure 10, show that the potential for power output available at Witch Farm is large in comparison with other successful projects, as might be expected from the scale of outputs that powered from this route, as we discussed earlier. So, except for environmental issues, this would be a very strong candidate for geothermal repurposing. However, the issues discussed indicate that careful thought is necessary when designing suitable geothermal end uses for Witch Farm and other projects within environmentally protected areas. And such considerations were beyond the scope of this study. Geothermal repurposing of the Stockbridge and Wilton fields might yield thermal power outputs of up to 638 kilowatts for Stockbridge and 251 kilowatts for Wilton. And these are comparable to mid-scale mine water geothermal projects, for example. However, the mine water projects are managed as components of integrated energy systems for seasonal heating and cooling, including summer storage of waste heat, rather than solely for heat supply. So it's difficult to see how this type of energy management might be combined with oil co-production, such as that of Stockbridge and Wilton. And again, analysis such as this is outside the scope of the study. And so the mine water sites are referred to there were Springhill and Bannon, excuse my pronunciation. So nonetheless, despite the constraints at each of these sites in terms of both the environmental barriers and limitations on some of the end uses of the heat, each of the investigated fields has the potential for sufficient thermal power outputs at high enough temperatures to be of practical use. So in conclusion, we've carried out a systematic screening survey of the data sets of onshore hydrocarbon wells in the UK and geothermal data to determine the most suitable candidate sites for geothermal repurposing from onshore hydrocarbon fields in the UK. GIS mapping model was generated, which integrated data obtained from the Oil and Gas Authority and data on the UK's geothermal resource. Of the 2,242 onshore wells reported at the time of conducting the research, 560 were recognised as having potential for repurposing, and 292 of these are currently operating, which would be considered the most optimal wells to repurpose. The results of this analysis identified the 10 other fields with the greatest potential for geothermal repurposing. The four most suitable candidates being Witch Farm, Stockbridge and Wareham in the Wessex Basin, and Wilton in the East Midlands Basin. Detailed investigation of the potential heat output that might be obtained during the remaining field life were carried out for Witch Farm and Wareham using the clean curve analysis. And from a technical and economic point of view, Witch Farm field has especially great geothermal potential. However, its location in a highly protected landscape limits the options for geothermal repurposing and excludes some possibilities, such as greenhouses for growing high-value crops, which would otherwise be feasible. Other potential end uses of its heat at distances of several kilometres away were identified, which would involve supply of heat to hotels and swimming pools in tourist areas in the south coast of England. But the cost of transporting to these locations might be prohibitive and requires further investigation. Nonetheless, the recognition of a potential geothermal heat output of around 90 megawatts at Witch Farm and hundreds of kilowatts at Stockbridge and Wilton indicate a promise and set of targets for more detailed assessment, offering the possibility of making useful contributions to the decarbonisation of UK energy use. So thank you very much for listening, and I welcome any questions. Thank you.
Thanks, Sean. That was a really interesting presentation. It's quite nice to see that potential in the UK is actually much bigger than we first had anticipated with the first sort of heat maps that are seeing sort of down the east coast. There's more heat there than we initially realised. I'm also impressed to see how much GIS and geology is in there. I'll never forget myself and Aaron giving you a crash course in geothermal geology when you first started your PhD all those years ago. So yeah, we can open the floor to any questions. So if people want to turn on microphones, cameras if you want to as well, and wave at us for questions. Anybody? So you've obviously done an estimation of thermal power for the Witch Farm in the south, even though there's some sort of environmental challenges there that might restrict what you can do or what an investor might be able to do. Have you managed to do any sort of thermal or even electricity potential estimations for anywhere else in the UK yet?
So we focused on Witch Farm and Wareham, and also done some preliminary calculations on some of the other high-ranking sites as well. See if I can just scroll back through to this table here, which highlights the 10 the highest ranking fields in the UK. Yeah, we did preliminary calculations of the potential thermal power output for each of those. They're included in the energies paper, which actually I don't have to hand at the moment. But yeah, the four most significant, or the four fields of the most significant thermal power output were Witch Farm, Stockbridge, Wilton, and Wareham, and the remainder were around about 100 kilowatts or less, given the smaller water production rates and smaller or lower bottom temperatures in the case of Whisby and Palmerswood, for example. But yeah, the data, the results are in the paper if you like to go and have a look at them.
Great, thanks. Aaron, did you want to ask a question there? Got your camera on, yeah.
Yes, I have. I have several questions. As we have several oil and gas repurposing projects in UK and in Canada, and for I'm doing mostly the same maps. And did you make any chemical analysis to understand the deep geothermal reservoir, like isotope analysis or geothermometer analysis? Sometimes repurposing of oil and gas wells could be more expensive than drill a new well. And we don't, in the real geothermal world, we don't want oil or hydrocarbon mix in the system. Did you make any cost analysis for this? For now, that's all I think.
Yeah, I noticed, sorry, Rob Westerby is in the audience, so he wants to jump in. He has been one of the co-authors of the paper with any response to this. But yeah, kind of detailed economic studies such as that on a particular site were slightly outside the remit of the work, which is more of a kind of high, at the beginning, it's a high level analysis of all fields across the UK. However, we were aware of the issues over the presence of the produced hydrocarbons with the geofluids. I don't know if you'd like to come in, Rob, with anything that may help.
Well, yes. I mean, one of the issues that we encountered was that the regulatory situation, which is quite complex, and that the onshore hydrocarbon wells in the UK are regulated by the OGA, the Oil and Gas Authority, and they would continue to regulate the wells if, say, geothermal energy was co-produced along with continuing to produce the oil or gas that's currently produced. And so in principle, such co-production might extend the economic lifetime of particular fields. For example, at Witch Farm, we worked out that if the produced water, the amount of produced water that is available from there is quite substantial. If that were used somehow for, say, heating greenhouses and substituted for burning natural gas, its value would be roughly about a third of the value of the oil that is being produced. So it's quite significant and could potentially extend the lifetime. On the other hand, if wells were repurposed so as to only produce with the intention of only producing geothermal heat and not hydrocarbons, then there would be the problem that they're currently connected to hydrocarbon reservoirs, and so there would be oil or gas in the output from them, which if that was not being used in any way would become a nuisance. And so trying to find a way through this regulatory situation is difficult, and some geothermal developers consider that it's insoluble, and that despite the cost savings that might be achieved by the saving capital cost of not having to drill new wells, it might work out overall cheaper across projects as a whole to ignore the existing wells and proceed with new wells that, being geothermal only, would not be regulated by the OGA and be covered by a much simpler regulatory situation and could be engineered more cheaply. So there really is this dilemma at the moment over how things are going to proceed, and can a way be found through this regulatory problem? And really, I don't have an answer. I don't think anyone does at the moment, but it's where the field is at the moment.
All right, wait, Aaron.
Yes. Okay. Thank you.
Yeah. Okay.
Yeah.
There's a question on the chat. Sorry, Aaron, were you going to say something then? My apologies.
Yep.
No. Okay.
No,
And there's a question on the chat from Carol. She's had some connectivity issues, so she just wants to sort of ask about if there was any work done on fluid flow in any of the areas, or if there's any data available on fluid flow because she's saying from what she knows from geothermal, it seems odd to consider heat flow in isolation from fluid flow. And I guess that would depend on whether you're looking at open loop or closed loop. But is there anything you want to comment on there, Sean, with respect to that?
Yeah, well, we're provided with data on fluid flow at which farm and Wareham, although yeah, we didn't actually get to the modelling stage of modelling the potential reservoir system. They're just given the time scales of the project actually, so yeah, we didn't get into that, but acknowledge that this would be necessary for a fuller analysis.
Sorry, thank you. I was telling my dog off for shouting at the neighbour. Thank you. Carol, I hope that answered your question there. I realise you might not be able to speak, so put in the chat if you want to expand on that. Ollie, did you want to ask a question?
Yeah, thanks, Sean. That's an excellent presentation. It's something that I've been talking to, having recently transferred over from the oil industry. This is something that's obviously very key in my mind, and talking to Professor John Underhill in Heriot Watt, and quite a lot of stuff he's trying to organise that with PhDs. But also being very familiar with the South Downs, and in fact the Singleton well, I used to live a mile away for most of my life, so I know the area well. And the other issue obviously with which farm might be in a area of natural beauty, but then Singleton and Storrington are all in the South Downs National Park, which is obviously another level above that. And I'm also aware that, you know, places like the Singleton oil well is purposely a long way from any habitation, and it's surrounded by a forest to kind of hide it. Is there, I mean, I'm assuming obviously you've done more of a subsurface review, and you're not really talking about the top sides of what kind of infrastructure that might be needed, like whether it maybe needs to go to ORC or something like that to produce more from a very low temperature. But I assume like the next step might be to look at these wells and do a kind of radial analysis of how close is it to infrastructure, how close it is to kind of agriculture. I mean, greenhouses is definitely something, and district heating. I mean, even my father's looking at trying to heat the parish church using geothermal energy. So there's definitely potential there. But have you looked any further than that, or is that just far beyond the scope of your PhD?
No, it wasn't beyond the scope at all. It was part of the initial idea for the work was to incorporate the kind of local heat demand into the screening, site screening analysis. However, it was getting access to the data to do that kind of high level study was difficult at the time, because for example, the UK's heat demand map was decommissioned a number of years ago. So I mean, that would have been ideal to overlay local heat demand around these oil and gas wells, to just give a kind of first order comparison or assessment of which wells are close to the areas of high heat demand. But we did look into this specifically for Wareham and Witch Farm. It wasn't included in the papers, but there was some preliminary analysis on just by applying like 5 kilometre, 10 kilometre buffers around each of the wells in GIS software, and on Google Maps, and just kind of a hand and pointed which wells are close to or which kind of local hotels or hospitals, that kind of thing, were close to the wells. But yeah, we kind of stopped short of doing a fuller analysis. But yeah, again, that would be the next stage. And it's the type of thing I've kind of done up in up in Scotland and in Glasgow from my own PhD research, looking at optimal sites for geothermal energy and how that can be tied to local heat demands. So yeah, that would be, if the project was longer than just the 6 months we worked on it, then yes, I'd certainly like to, and if the data was available, which wasn't at the time, but yeah, would be to look into that.
Thanks.
More questions from anybody at all? No?
I guess one more follow-on question of that. Oh, sorry, Maddie's about to say something, but I just wanted to ask: can you adapt that for the offshore environment? Is it easy enough to use the same methods that you've used and use that for the whole UKCS?
Yeah, we did look at that. I didn't personally look at it, but we, following on from this work, we did have some masters or level students at the University of Glasgow who looked into the offshore potential for repurposing offshore wells, and also tying that in with hydrogen production storage, tying in with offshore wind sites. Again, Rob might be able to discuss that more than I was, more than I am able to, because he was one of the supervisors of that project. Yeah, I think a similar methodology was used, whereby kind of relatively simple GIS comparisons and assessments made of the location of offshore fields to the proximity of offshore wind sites, and yeah, also the locations of potential pipelines transporting onto the onshore as well. So yeah, that work hasn't been published to my knowledge. It was presented at the UK Geothermal Symposium. 2017 it was now. So yeah, again, there's potentially some future work that can be done as well, doing a fuller study of that.
Thanks for that. Sorry, Maddie.
Maddie, did you want to ask a question?
No, sorry, I didn't have a question. I just thought I'd put my camera back on and say thank you very much for a really interesting presentation. That's great.
You're welcome.
If there are no more questions from anybody, I'm conscious of the time, and we also have another wing meeting at 5. No, I think that's everybody. Great. Well, thanks, Sean, ever so much for the really interesting presentation. I'm sure if people think of something afterwards that they can follow up either via myself or directly with you if they caught your email address there.
Yeah, I'll set that up again if I can.
Yeah.
There we go.
Yeah, so just at the bottom, for anybody who wants to grab that quickly, or like I say, you can reach out to Wing if you want to raise any further questions on this really interesting work going forward.